So proof by cases is really similar to the method of exhaustion. The hardest part sometimes is just figuring out what the cases ought to be. In the last example, we determined that we needed to test n equals 2, 6, 10, 14, and 18. In a geometry class, if you have a statement about angles, then your cases might be to test acute, obtuse, and right angles. If you're dealing with a statement about real numbers, you might test positive numbers, negative numbers, and 0. If you're dealing with a statement about integers, you might test even integers and odd integers. We are going to do some complete proofs by cases, but largely we'll use this type of reasoning to determine the truth of a statement. Let's take a look at this first example, which is not mathematical at all. Every student in MHS will take a standardized college entrance exam. Well, I could ask every student in the school if they plan on taking this sort of standardized test, but that would be way too time-consuming and too tedious. So is there a way I could divide the student body into large groups? Well, of course. What I could do is divide the student body into sophomores, juniors, and seniors, because that's the students at Maryville High School. So when I start to think about it, I realize the students who are sophomores take the practice ACT, which is the plan test. And then the students who are juniors have to take the real ACT. That's dictated by the state. Now, once the students are seniors, they either retake the ACT if they weren't real happy with their junior score, or if they are really happy with their junior score, Maryville High School asks them to take the SAT. So in every case, the student will take a high-level standardized college entrance exam. So overall, the statement's true. Let's look at a proof by cases problem that has something to do with math. So if d does not divide 6, then I to the d factorial power equals 1. How about we look at scratch work? Now, I want to remind you that if d divides or does not divide into 6, we need d to be a positive integer. So I have listed all the positive integers here, or at least the beginning of the list. Now let's figure out which ones do divide into 6 and mark those off the possibilities. Well, 1, 2, 3, and 6 all divide into 6. So the way I see it, we can test 3 different possibilities. So I'll say that case 1 is that d would equal 4. In case 2, d equals 5. Now, what I want to do for case 3 is lump d equals 7, 8, 9, 10, and so forth into one large case. So let me say d would just be an integer larger than 6. Now, if d is equal to 4, d factorial is equal to 4 times 3 times 2 times 1, which is equal to 24. Then I could say that I to the d factorial equals I to the 4 factorial. That's I to the 24th. Now remember, we know if 4 divides into your exponent evenly, then I to the 24th winds up being I to the 0 power, which is equal to 1. So when we test d equals 5, we know that d factorial is simply going to be 5 times 24, which would be 120. So I to the d factorial equals I to the 5 factorial equals I to the 120th power. And just as we said in case 1, 4 divides into 120 evenly, so I to the 120th must be 1. So my first 2 cases are giving me a true statement. Let's look at the third case. Now, if d is greater than 6, then I can say that d factorial is d times d minus 1 times d minus 2 until I get down to 4 times 3 times 2 times 1. Well, let me say then that d factorial would be this 4 times the product of the d minus 1, d minus 2, and all of the other integers in the list. Well, the product of several integers is still an integer. So let's call that integer k. That means I to the d factorial equals I to the 4k power. And just like we said with cases 1 and 2, 4k is a multiple of 4. That means I to that power must be 1. So to review, we are going to suppose that d does not divide 6. We figured it out. That means d equals 4, 5, or d is greater than 6. So those were our 3 cases. In each case, we tested I to the d factorial power. In the third case, we had to talk a little bit more about what d factorial would equal. But we also figured out in that case that I to the d factorial power is 1. So if I'm getting a true statement for the 3 individual cases, then the overall statement is true. So let's look at one final proof by cases that has to do with calculus. So if we read the statement together, it says if f of x is any twice differentiable function, that just means that f prime of x and f double prime of x exist, such that f double prime of a is less than 0. What do we know if the second derivative is negative? The f of x must be concave down at x equals a. Then the tangent line approximation at x equals a overestimates f of a plus h for very small values of h. That's a lot of words. So let's see if we can break that down. So I have already started to list cases. I know that a function could be concave down, and I'm using shorthand notation, and the function could increase. So I might have, in this case, a function that looks like y equals the square root of x. I also know that a function can be concave down and the function can decrease. So in that case, I might have y equals the square root of negative x, where I simply translate or reflect the original parent function over the vertical axis. All right, some people might think that this is all the cases there are, but let me remind you that if f of x increases at x equals a, that means f prime of a is positive. And if f of x decreases at x equals a, that means f prime of a is negative. Does that make you realize there's got to be a third case? And our third case will be f of x is concave down, but f prime of a equals 0. So this would be the case where maybe I have a piece of a function that looks like a parabola, but at x equals a, my tangent line is horizontal. So let's call this point of tangency a f of a. Let's call this point of tangency also a f of a. But here, since f prime of a is negative, the tangent line has a negative slope. Here, we've got a f of a, and my tangent line has to have a positive slope. Now I'm going to blow one of these up for you so you can see what's going on a little better. So I've expanded the first example. And remember, you were asked something about f of a plus h. For small values of h, that just means that we're going to move from a rightward to an x-coordinate of a plus h. So I'm going to make this point have an x-coordinate of a plus h, and its y-coordinate will be f of a plus h. Now, if I look at the tangent line, the point on the tangent line that has the same x-coordinate, a plus h, will be directly above or below, in this case, above the function. So the y-coordinate of this point is higher than the y-coordinate of the point on the function. So the point on the function is the f of a plus h. So this y-coordinate is the tangent line approximation. This y-coordinate's the function value. So the tangent line approximation is higher than the function value, meaning the tangent value overestimates the function value. So we see here that I've written up case 1 a little more neatly. Let's look at the other two cases. In this case, we have a decreasing function that's concave down. We already had our point a f of a. Moving to the right along the black function, we get our new point a plus h f of a plus h. The point on the red tangent line that's in green, directly above it is the tangent line approximation. And once again, this green tangent line approximation is higher than the blue point on the function. So once again, the tangent line approximation does overestimate the function value. Our final case is similar. Even when the tangent line is horizontal, the point on the tangent line that represents the tangent line approximation does exceed the point on the function. So in every case, the statement is true. This concludes our lesson. I want to let you know what's going on for the rest of today and tomorrow. So today we're going to get together in our groups of 3 or 4. We're going to do part 1 of the worksheet, which has quicker, more direct practice problems. Tomorrow you'll reconvene in those same groups of 3 or 4, and we will do more challenging problems. You'll get a little more true-false action going there. But tomorrow we're also going to do the introduction to modular arithmetic, and you'll have a part 3 of the worksheet that we'll complete tomorrow. But don't you worry. Besides today and tomorrow, you're going to get a lot more practice on modular arithmetic and proof by cases.